So, the first section of this unit, we are going to be talking about scientific and engineering notation. Let's start with scientific notation. Consider the numbers 1, 10, 100, 1,000, 10,000. Those aren't too difficult to read, right? We can also go the opposite direction, talk about a tenth, a hundredth, a thousandth, a 10,000th. Still not too bad. But what if we had a ton of zeros? How many zeros do we have in this number up here? 3, 6, 9, 12, 15, 18. Do you even know what number that is? I'm not entirely sure I do. And I don't even want to count the number of zeros in this number. These start to get really tedious to read when we get a lot of zeros to deal with, and that is why sometimes it's better to use scientific notation. So with scientific notation, we are working with powers of 10, and we're going to be writing these powers of 10 in exponential form. So we're going to have 10 to some exponent. So let's convert these tens in exponents to decimal notation. So our first one, we have 10 to the fourth. So that is 10 times 10 times 10 times 10. That's going to be a 10 with 4 zeros. So let's write that, 10 with 4 zeros. So that number, and I like to put commas in every 3 zeros, that number is going to be 10,000. Let's look at 10 and 3 zeros. That's 1,000. 10 and 2 zeros, we all know, is 100. 10 to the first, that's just going to be 10. 10 to the 0, well, we learned last unit that anything to a 0 power is simply 1. 10 to the negative 1 is going to be 0.1. 10 to the negative 2, 0.001. We're going to keep our 1s. They're not going to turn into 2s. 0.0... Sorry, my finger is in the wrong place. 10 to the negative 3 is 0.001. 10 to the negative fourth is 0.0001. So do you see a pattern here? When we talk about positive exponents, we have 1 followed by the number of zeros that are found in the exponent. So this guy has 4 zeros and has 4 in the exponent. 3 zeros, 3 in the exponent. So look at the number 1. It has 0 zeros and a 0 in the exponent. So positive and 0 valued exponents are pretty simple to figure out. Let's take a look at the negative exponents. We have a 0 before the decimal point, but no 0 after. And the same with the next one. We have a 0 before the decimal point, 1 0 after, but we have an exponent of negative 2. So the zeros after the decimal point are 1 less than the absolute value of the exponent. Or if you want to think about it this way, the first 0 is before the decimal point, so we do technically have 1 0. We have 1 0 on 10 to the negative second to the left of the decimal point. And we have 2 zeros total, 3 zeros total and 10 to the negative 3, 4 zeros total and 10 to the negative 4. So the key is to try to remember when you have negative exponents, you have to count that 0 that's to the left of the decimal point if you want to match zeros with exponents. So what does this have to do with scientific notation? Let's consider a number like 50,000. 50,000 is not a power of 10. It has 5 at the beginning. So what we're going to do is we are going to take that 5 and multiply it by a power of 10. And then we're going to take that 5, multiply it by the exponential value of that number. So instead of 1 with 4 zeros after it, we are going to have 5 times 10 to the fourth. And that leads us into our definition of what scientific notation is. So a number is written in scientific notation if we have a constant, and remember a constant is pretty much any number, but that number has to be a single digit. It cannot be 0. It has to be at least 1, and it has to be less than 10. So we could have 1 times 10 to the 4th, and that would be the scientific notation of 10,000. We could have 9.99999 as long as there are a finite number of 9s, and it would still be less than 10. So the digit, the very beginning, simply has to be greater than or equal to 1 or strictly less than 10. Let's look at our first problem here. The mass of Earth is approximately, oh my goodness, I do not know that number. I don't know if any of you do, but it's a lot of kilograms. The mass of Mars is also a lot of kilograms. Can you determine which mass is larger? So let's take a look at this. How many zeros are in the mass of Earth? I can count by 3s because thankfully we have commas in here. So let's count these. There's 3, 6, 9, 12, 15, 18, 21, 22 zeros. So that's going to be 597 times 10 to the 22. But 597 is greater than 10, so we still have to move our decimal place a couple more places. We need this number to be greater than or equal to 1, but strictly less than 10. So our decimal point is currently right here. So we're going to move it 2 more places. So that's going to give us 5.97 times 10 to the 24th. When we move the decimal place to the left, our number is going to increase. Our exponent, I should say, is going to increase. If we move it to the right, it's going to decrease. Let's look at Mars. How many zeros do we have for Mars? 3, 6, 9, 12, 15, 18, 21. 21 zeros. So 639 times 10 to the 21. And again, 639 is greater than 10. So we have to move our decimal place a couple more times. 1, 2. So that is going to make it 6.39 times 10 to the 23rd. So let's compare these numbers. This one is Earth. This one is Mars. Can we determine which number is greater? Well, if we look at the first part of the number, it appears as though Mars was greater, but Earth has a higher exponent in the tens value. So that is actually going to make Earth the larger mass. So the mass of Earth is larger. You may be familiar with the term order of magnitude. This refers to the powers of 10 of two numbers. So we can say that Earth is larger by an order of magnitude of 10. Let's look at problem 2. The radius of a hydrogen atom is approximately a tiny number. I can't tell straight off just from looking at it what number this is. The radius of a chlorine atom is approximately another tiny number. Can we tell which radius is larger? So let's count the zeros. Don't count the 0 that's to the left of the decimal point, just count the zeros that are to the right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. I'm going to double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this means that we have 0.53 times 10 to the negative 10. Now it's a negative 10 because the zeros are to the right of the decimal point. However, this number is not greater than or equal to 1, so we have to move the decimal place one more time. So we're going to move it over here, and that's going to give us 5.3 times 10 to the negative 11th. Because remember, when we move the decimal point to the right, the number is going to become smaller, and negative 11 is smaller than negative 10. Let's look at the chlorine atom. How many zeros does this one have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 0.18 times 10 to the negative 9. Again, this number is not greater than or equal to 1, so we're going to have to move the decimal place one spot. So this is going to become 1.8 times 10 to the negative 10th. So to determine which radius is larger, we have to look at our powers of 10. That's where we want to start. So which one is larger, 10 to the negative 11th or 10 to the negative 10th? 10 to the negative 10th is going to be the larger radius because we're talking about negative exponents. So we will say that the chlorine atom is larger. By a magnitude of 10. Scientific notation is very helpful for really large numbers and really small numbers. So that's the main reason that we're learning this. In your programs and in your future careers, you may be dealing with really large or really small numbers, and it may be more convenient to look at them in scientific notation. So I'm going to have you all work on problem 3, converting each of these numbers to scientific notation and from scientific notation to our standard decimal notation. So I will see you next video.